Dr. Allain, my name is Bo Gibbs. This is reassessment number 5, forces in circular motion. We have the question, and of course the first question said, what is the centrifugal acceleration of the group? First we know that of the group going around the London Eye. So first we know that the eye rotates twice in twice in 1 hour, and we have to convert that to seconds. So T equals 1 hour over 2, and of course 3,600 seconds are in an hour, divided by 2 equals 1,800 seconds per rotation of the eye. And next, we have to get the radius, and so we know that the diameter is 120 meters, and divided by 2, of course, that's 60 meters for the radius. So we have to get the circumference after that, and that's 2 pi r. Now 2 pi times 60 equals 376.99 meters. So the speed of the group going in the capsule going around the London Eye is velocity equals circumference divided by time, or 376.99 meters divided by 1,800 seconds. It means our velocity is 0.21 meters per second. So the group moves at a constant speed in a circular path, and the capsule's acceleration is always directed towards the center of the wheel, and its magnitude is angular acceleration equals velocity squared over r, or 0.21 meters per second squared divided by 60 meters, and that we get is 7.35 times 10 to the negative 4th meters per second squared. It's a horrible acceleration. B, we are asked to find what forces does the passenger capsule exert on the travel group at the lowest point. So draw a little picture. That's the capsule at the bottom of the circle, and that's where the forces are pointing. The acceleration's up. It's always got, at the lowest point, it's pointing up towards the center, and that's what we talked about in the last problem. The mass, I said originally there was 25 people averaging about 86 kilograms, so that's about 2150 kilograms, or 2,150 kilograms, excuse me. So you have the force of the capsule minus mg equals mv squared over r. That equals mv squared over r plus mg. So 2,150 kilograms times 0.21 meters per second squared over 60 meters plus 2,150 kilograms times 9.8 meters per second squared gives us 21,072 newtons. So the capsule pushes up on the group with a force of 21,072 newtons. A lot of newtons. When the capsule is at the highest point of the rotation, the acceleration is downward. There it is, the picture again. This way the A is pointing the opposite direction. The problem is going to be similar to part B. In fact, the same forces, is just that it's just how you set them up. So mg minus F capsule equals mv squared over r, or mg minus mv squared over r. So you just plug in the same little problems, and you get 21,068 newtons. So the capsule pushes up on the group with a force of 21,068 newtons. Excuse me. So, oh yeah, I just lost my train of thought, sorry. When the capsule is halfway up or down, the net force still points towards the center of the circle. However, the direction of the acceleration is got to be horizontal, as it shows in the picture. There's the people in the capsule. So you got to find the vertical component, which is mg. So you type the kilograms times the meters per second squared, and you get 21,070 newtons. You find the horizontal, which is just mv squared over r. You get 1.58 newtons. Now just square the x and y and find the square root of it. You plug that in, and you actually get something very similar to x, which is 21,070.00006 newtons. And this force is directed at an angle above the horizon, given the following equation, and at 90 degrees. Thank you.